So if people are waiting, I encourage you to go and download the slide deck that we're going to be using will be numbered 3.4 version 3. So I could put that in the, Giuliano, maybe you can also put that in the chat, that we'll be using, and also the instructions for downloading the demo that we have, which is also under day 3, module 4. I need to do the breakout. If things went a little fast yesterday, I appreciate your patience. You'll have plenty of opportunity to go back over that material again. Thank you, AJ. I appreciate that. One of the things I was saying earlier with talking to Tony is that one of the challenges of this course, and also one of the virtues of this course, is that we get people who come from all different backgrounds. We have literally over the years had pure mathematicians, surgeons, computational biologists, chemists, MDs who are not surgeons, toxicologists, and we've had everybody from high school students to emeritus professors. And so nobody comes to the course with the same background.
Yeah.
And we've been looking at the polling that we've been doing about modules. And in every module, there's some people who feel it's going much too fast, and some people feel it's going much too slow. Some people feel it's covering too much material. Some people feel it's covering too little. We've thought about trying to fork the class to have an advanced class and a more beginners class.
It's definitely hard to keep up with building the model in real time, and especially when whoever's doing the instruction sort of deviates from what is in the slide or in the uploaded model, which is used as a reference. But in the end, it's, I guess at some point we have to just go back and redo the whole thing, build the model slowly at a pace that works for us. Otherwise, because what I found was I certainly have a little bit of a hard time doing it in real time. And then if I'm engaged in trying to deal with whatever peculiarities of loading, I miss what the person is saying, and then I'm completely lost. So I have to make sure I just keep paying attention, because that's more important than trying to write it in real time, I think.
Right, I think that's tricky. I think coding live is hard.
Yeah.
On the other hand, I think having some exercises is essential. And so balance between those two things.
Yeah.
I thought actually Giulio Belmonte did a very good job.
I absolutely agree. Absolutely agree.
And I think the way Giuliano and Gilberto presented it, if people are familiar with the material already, then that works. But perhaps we're going to go back and rework those slides So instead of covering that material in one module, it takes 2 or 3 modules, and you
Yeah,
have more.
yeah.
Uh,
No, you're exactly right. For my level of competence or incompetence, whatever you want to call it, Julio's was definitely just the right pace for me. It was very well done. Yeah,
and I appreciate. I mean, we do take those questionnaires seriously,
yeah,
and so for next year we'll go back and rework those modules where people seem to have trouble following. We
yeah,
always try out new ideas. The thing that happened last year was, of course, we taught the whole course around the idea of building a COVID model.
yeah.
Uh, and then this year, people asked us to go back to the more developmental biology focus.
Well, I
And
certainly appreciated that.
and but that meant that we had to redo all of the lectures.
Yeah, yeah,
So I thought last year we actually had quite a good organization.
yeah,
And the slide decks were very well organized, but we couldn't use them.
yeah.
Uh, so uh,
No, and
so we
it was a good alternate way of doing it because you did one very complex model very thoroughly and step by step. But I mean, first of all, it was much more new to me then, so I got lost much more easily. And so this year, it's been much better for me.
well, we appreciate you coming back. I was saying to Tony earlier that I always say the same thing, which is that if something is actually worth hearing once, it's worth hearing twice.
Yeah, yeah. No,
It's either not worth hearing at all, or it's worth hearing more than once.
and this year I have managed to recruit a very nice postdoc who's he didn't actually have that much background in CompuCell 3D, but he's worked through last year's workshops. He's attending again, Abhishek. He's the one who's on my slide. So we'll work together, and we're really happy to have been on this course together.
Well, I appreciate it very much, and again, I appreciate everybody's patience with doing it virtually. Has doing it in person makes it easier when, in the sense that if people have issues, in the old days we'd have a room with 20 people in it. We had a beautiful conference facility for it, with each person at a big table, and so there was enough room that we could the instructors could circulate and sit with each group
Right.
and work with them individually. We're trying to do that with the breakout rooms, but it's not quite the same. On the other hand, we're also able to have people from Europe, people from Asia who wouldn't be able to attend if it were in person. So there always are trade-offs.
No, it's true. I think this is the net value of the virtual meeting has been definitely positive. I'd say the number of people who can attend much more easily, not only in terms of the cost, but the logistics because of COVID has made it so complicated to travel that it would have been impossible.
So there was a question in the chat: are the past schools archived and accessible? The slide decks and the videos should be available. We can they should be on the CompuCell site if you click on past meetings, and at least some of the videos are up on the YouTube channels. The main problem is that we don't have funding for supporting the sort of the AV and things. It's quite time consuming and expensive to edit the videos. And so we need to go back and do some more editing of the videos. But yes, the past workshops, last year in particular, all of those the videos are available, and all of the slide decks are available. So if you're interested in all the exercises. And so in last year, we started out with a viral dynamics model, an OD viral dynamics model of a simple infection, in fact, SIR type in-host model, the kind of a model that people like Alan Perlson write. And then we took that model and converted it step by step from being an OD model to being a spatial model of a patch of tissue being infected. And
that's great. I have another question, and this is to do with the parameters, when I deal with multi-parameter system, the right, in quotes or not, parameter set is not unique.
That's absolutely true.
And the only way to verify that it has certain reality to it is by comparing to experiment or to the literature in large. And that brings a lot of questions because some of the goals of these simulations is to save time of expensive experiments or to design the next ones.
So those are very fundamental questions, and I'd love to. I have a whole series of lectures on those issues, which I'm not able to give because there's no time. If we had, if we were, when we do this in person, we actually have more, the days are quite a bit longer. But we figured that 6 hours of sitting watching Zoom a day for 5 days plus 2 plus 1 for 8 days was enough. And so
more than enough.
Right. When we do it in person, we typically start at 9 a.m. and end at 6 p.m. And then we have a little bit more time to cover some of these more very important issues. These models are always overfitted. There are many sets of parameters that will do the same thing. And there are some fundamental questions about how you do validation. One of the reasons we did the course last year around doing an ODE model first and then turning it into a spatial model is that fitting parameters for the ODE model is easier. And then you can actually know that the parameters, at least those parameters, are correct. And so there are a whole series of issues about how you do parameterization of these complex models. If you're interested in hypotheses about whether mechanisms exist or not in a system, then often the exact parameter values matter less. But it's absolutely true. I'm delighted to have some questions because the whole point of this early period was to have this kind of conversation. So I'm glad that on day 4 we're having it. This kind of issue is profound, and I don't have a good answer for you. Something that we've been doing a lot more of is that we typically, the CompuCell was designed so it would run on your desktop in real time so you could see your results and play with them. And so it was really created to be an exploratory tool. However, these days we tend to run it on large clusters. We'll run tens of thousands of replicas, hundreds of thousands of replicas. And so, for example, when we showed the COVID simulation where we did a remdesivir dosing simulation, that would involve thousands and thousands of replica simulations where each parameter set was run multiple times because they're stochastic models. And then you would then scan multiple parameters simultaneously. Josh and a team at Pittsburgh have been building a nice interferon model. And again, what they did was they started with a experimentally validated ODE model of interferon response, and then asked the question, when you move that non-spatial model, which is deterministic and doesn't take into account heterogeneity in tissue, and you put it in a spatial context, what changes? And so they were simulating plaque assay, viral plaque assay growth in the presence or absence of interferon pre-stimulation. And in that case, you can nail down at least some of the parameters pretty well. So it very much depends on what kind of experiment you're talking about, what information is available. Another slogan that Tony's heard and AJ's heard is that building these kinds of models is brutally revealing of what you don't know biologically. And very often when people come to my office, I used to have a wet lab. Since COVID, my wet lab is gone. But I did plenty of developmental biology experiments in my day, and I did microfluidics, these kinds of things. But you would say to people, they'd have an idea about a project, and you'd say, these are the things you need to know to be able to build a model. And the response would be, well, if I knew those things, I wouldn't need the model.
Yeah. Another question, if I may.
Please.
Can I take distance and think about doing PCA analysis in the parameter space?
You certainly can. The only problem with that is that the simulations tend to be long, and so you have to think about it efficiently. I mean, one of the big problems with using these kinds of models is if the simulation takes something. There was a question in the chat about can you multi-thread CompuCell? The answer is yes. If you have a high-performance computer with 64 cores, you could say run it on 128 threads, and it'll run about 60 times faster. And that's an option in the beginning of the XML of the CC3D ML, the markup language. You could switch, and that works really well on high-performance computers. But I was going to say, one of the issues that we very early version of CompuCell actually had an MPI deployment where you could actually spread out one computer simulation over many boxes. And people didn't use it at the time. This is 20 years ago now. But when you're doing optimization, you have to do sequential runs. And so if each simulation takes 2 hours to do, and you have to do 1,000 generations of optimization because you're doing something with AI, or you're doing something with even a classical optimizer, then that means that optimization takes 2,000 hours to run. And so we tend to use things like particle swarm methods, which are less efficient in terms of total computation time, but are more efficient because they require fewer generations to converge. And so you have to think about how to do your analysis. There's a paper that Jim Sluka did with Xiao Fu, who's now at the Crick in London, who's a graduate student, excellent graduate student in this group, where they did do detailed sensitivity analysis of their liver toxicity model. But that's single factor analysis. That's not doing full PCA. And the interferon paper that Josh has done, they also did sensitivity analysis, but again, not full PCA. But there's certainly no reason. CompuCell now is callable. It runs on a cluster. And so provided that you can return a metric from your simulation that gives you a residual, you can call a CompuCell simulation from a Python library that does PCA and returns a residual. It'll take a long time to run, and you'd like to have one that uses a cluster deployment so it can run multiple replicas simultaneously, but that's possible. That's outside of the scope of this lectures this week. Although Jim will talk maybe a little bit about cluster deployments. TJ could do that. But if you're interested in how to do that, TJ has thought about it a lot. And we'd certainly be very interested in seeing more formal ways of doing it. So I'd be very interested to talk to you about it. Any other comments, questions?
Thanks for that long answer.
I'm sorry, I didn't mean to go on too long.
You're doing very well. I'm not in position to give you compliments, but you're doing very well. By the way, I was lured to the whole thing by your talk, I think 2 weeks ago in Toronto.
Oh, well, thank you.
And Maria, I'm not sure if Maria has the time to participate. I didn't see her or heard her. But I'll report to her about the experience, which I have in the so-called no hands-on mode. I'm the one who is doing telling you all the time, not doing the exercise. Because as AJ says, I'm trying to think what's going on here in the big picture. Okay, the details I may or may not ever even deal with, but that's a different story. So Maria, I'm sure, will appreciate this information, and I'll make sure that she's still with it.
I know she showed up yet the first day. I saw her on the call the first day.
Yeah,
I don't know if she had.
That's called time pressure of managers.
Yes, well, that's the one advantage. That's another advantage of doing it in person, that you're not distracted as much.
Sure. Yeah.
It is hard to do it, and I appreciate people's patience, because I wind up running the Zoom sessions, which means I don't have as much time to interact with people, because I'm essentially having to manage the meeting, and it does take some time. Pedro's been doing a great job on the meeting management, and Giuliano as well. But it actually does take some effort to manage the Zoom. And that's, we appreciate that. So there's another question. How do you fit the value of the energy for different cell types? So traditionally, we would start off this course with what a physicist would call the hydrogen atom, which is only a joke a physicist would understand, which was the cell sorting simulation. And I actually showed that at the very beginning of the first lecture. And we moved away from that for all variety of reasons, mainly because it was a bit of a dead end in terms of where it went. But the cell sorting simulation asked the question, and it's what the whole CompuCell thing started back in 1993, actually earlier than that, 1992 even, when there was a series of experiments. There's a classic series of experiments going back more than 100 years, where you take two cell populations, embryonic cell populations, you mix them together, and they sort out so that one forms a clump in the middle, and the other goes into a disc around the central clump. And the late Malcolm Steinberg from Princeton, who was a wonderful man that I worked with, I never worked for him formally, but he was sort of a mentor to me for many years, did a whole series of experiments that showed that the sorting order of the tissues corresponded roughly to the adhesivity of the tissues, the contact energies. And he came up with what was called the differential adhesion hypothesis of embryonic organization. Now, in reality, embryonic organization is more complicated than that. In the first place, when two cells come together, the adhesion between them changes over time as they form junctional adhesion structures, as the cytoskeleton changes, and so on. And secondly, cells aren't passive. And so there also are things like apical rings, contractile rings, and there's active contraction. So there's also a differential contraction hypothesis. And that's especially prominent in Drosophila embryos, but happens in all embryos as well. But the original version of CompuCell was written to simulate differential adhesion, reorganization of tissues under differential adhesion. And what you find is that what matters is the order of the energies. The most cohesive things go to the middle. The least cohesive things go to the surface. If the adhesion isn't sufficient, the cells spread out the way Giulio showed in his demo on the first day. And so you have a situation in which the order of the energies matters a lot. And if you make the energies too large, you can have artifacts where things freeze on this lattice that we work in. If you make the energies too small, you have situations where the cells fall apart into dust. But over a very broad range of energies, surface energies, contact energies, provided that the order of the energies is right. The more cohesive things have lower contact energies, the less cohesive things have higher contact energies. As long as that order of energies is right, you get the right dynamics. And then you can fine tune it by doing parameter fitting to get the exact ratios. And so that's actually a nice set of exercises to do, but it's time consuming because the cell sorting simulation, see, these days with modern computers, it runs quite fast. In the old days, running one of the simulations took quite a while, and so running enough of them to explore that parameter space was time consuming. So does that help a little bit with that? But one thing that we've talked about for years and never quite gotten to is to switch from this contact energy plug-in to this contact local flex, which is based on the number of molecules of each type. And that's much more natural because then each cell can have a different number of cadherins or a different number of integrins. And there's nothing intrinsically difficult about it, but you have to calculate then, if I want this energy hierarchy and the functional form of the adhesion is this, then I have to back out what are the number of molecules I need, what are the parameter values. And that it's not hard, but it's a calculation that takes a while to do. And we could either show you a result and have you do it, in which case you don't learn very much, or we could walk you through how to do the numerical calculation, but that would take an hour and a half to just show you how to do that calculation. It's not hard, but it's arithmetic. And so for the purpose of this course, we decided to stick with the older system of contact energies. But for example, I have a slide deck on cancer evolution, simple models of cancer somatic evolution, where the adhesion between the cells is determined by the number of cadherins and integrins. And then as the cells mutate, they change their numbers of cadherins and integrins, so the amount to which they adhere or don't adhere changes. And so that's actually a pretty simple example of using that. And the manual has a pretty good demo of that, of how to do it. And so that's something, if somebody's doing a project, a hackathon project, we could definitely work with people individually on how to do that. We need to make some slides and a tutorial on how to do that, probably. It's a good suggestion. There was a question about increasing the output frequency. Will your simulation be faster? No. Oh, well, okay, there are two questions there. One problem in CompuCell is that we're a little bit trapped by some of the terminology that was written down 30 years ago when we didn't know this would be continuing. And so there are terms like temperature that really shouldn't be called temperature, but we're stuck because that's what everybody in the field uses now. Another thing that happened in CompuCell is that there are things called frequency, which are actually periods. So the output frequency is actually the interval, the period between outputs. And so the question is, if I increase the output frequency, will the simulation run faster? If you actually increase the frequency, the simulation will run slower because it takes time to draw each image. If you increase the number of the output frequency, which is actually making the frequency lower, increasing the interval between outputs, it will speed up the simulation. And one thing that's a minor annoyance of Python is that the print statement takes a lot of time to execute. I don't know how that happened. It doesn't take time in C++, it doesn't take time in Fortran, but it does take time in Python. And so when you're printing a lot of material to the console, that takes some time, and you're usually better off debugging with that, but then turning those print lines off if you're going to run in production mode. All right, any other questions? I'm really glad that we're having such a lively discussion this morning. I appreciate it very much.
I had posted a question earlier on, but maybe you can address it later it's about comparing CC3D and Morpheus to understand the strengths and weaknesses of both. So it can help us decide for a particular problem whether one platform is better suited versus the other.
So we work a lot with the Dresden people. They're good friends. And Morpheus has a beautiful scripting language. It has its own scripting language, though. And the advantage of the Morpheus language is that it's very elegant, and it's in many ways very simple. And there are certain functionalities that Morpheus provides that are simpler to use than in CompuCell. The disadvantage is that because it's a unique scripting language, it doesn't integrate as well with the functionalities that Python has. You don't have an import NumPy. And so I would say that we've actually tried to learn from some of the things Morpheus has done. And Giuliano tried to write a converter between the Morpheus model specification and CompuCell. And you can actually convert quite a bit, but not all of it.
Yeah, the hardest part are events, so if statements in Python. There are ways to do that in Morpheus, but I don't really remember how to. But that conversion is tricky and hard to do.
But just before the lockdown happened, we were actually in Dresden for a week working on this problem. And I would say that CompuCell is a little bit more flexible, and it does support some features that Morpheus doesn't have. So for building models quickly, they're probably comparable. Maybe Morpheus has some advantages.
Morpheus is a bit easier.
But I think you bump into some limitations. Although the Dresden people are great, so if you point the limitations out to them, they'll work and extend the code. But we've dreamed for a long time of trying to merge the two packages, because there are these unique features on both sides that are really very attractive.
So I had a particular question, in terms of some of the things we're trying to do where we want to get apical constriction.
Yes.
With that particular phenomena, how do they, because in CompuCell you suggested that we need to make a hybrid cell of lateral cells and apical cell and a basal cell.
Yes.
Is that different in Morpheus, and is that a different type of solution to that kind of a phenomena?
I don't know. I apologize. I don't know how they do it. We will show how to do it tomorrow.
Yeah, I'm looking forward to that.
Okay. All right. Well, I guess actually it's 10:30, so it's actually our official start time. Let me quickly walk through our outline for today before we get into the main lecture. Appreciate everybody coming back. Very much appreciate you sticking this out. Our schedule has changed a little bit, clearly. We are going to start now with module 3.4. And even though it's in the place of module 4.1, it's going to keep the number 3.4. And so I strongly encourage you now to download the demo. Juliana, if you would post the link to the demo again. Download the demo, and if you're using NanoHub, please upload it. I will quickly walk you through that, but this whole lecture will be built around that demo, and it's critical to have that demo up on your computer if possible. Okay. After that, we will have a hackathon teaming discussion. Somebody asked if they could do updates on the hackathon team results. And so we're going to do that. We're going to have first 4 additional hackathon ideas from people who wanted to present. I hope they're going to be here. They said they would. Who wanted to present Tuesday and weren't able to. And then I will run through the slide decks for the people who presented before. And if you want to ask questions, make comments, suggestions, that's fine. If you want to set up some breakout rooms to meet with people individually, that's fine too. Anything we can do to help with teaming, that'll be good. And then whenever we're done with the hackathon section, we will go forward and begin to build subcellular network models using the antimony tellurium language and coupling them to cell behaviors. And so Joshua will be showing those. And depending on how that goes, we will either show how to do Boolean network modeling integration using MabBoss, and that may either happen this afternoon or tomorrow morning, depending on how the schedule works out. So again, I will start my lecture in just a minute, and then we will have our usual break. We'll have the hackathon teaming. When we're done with the hackathon teaming, Josh will take over and begin his presentations of the subcellular model integration. All right. Are there any other questions before we start? Again, this module is still numbered 3.4, even though it's in the 4.1 slot. So the schedule will be slightly out of order. We're going to be module 3.4, module 4.2, and then continuing with module 4.1 because we ran over a little bit yesterday. Each year we try out some new lectures. Some are wonderful, some need improvement, and that's why we keep asking you these questionnaires about your experiences. All right.